Hello, welcome to this lesson in Mastering Statistics. We're going to continue talking about p-values. In the last section, I just defined what a p-value is, which, just to remind you, is the probability of getting a data point or a sample point more extreme than the data that you collected for your hypothesis test. So it's basically going to be in the tails, either the left or the right, more extreme than the data that you've collected. If you haven't watched that last section, you have to do that right now. Now, we did a lot of work in trying to figure out how to find the p-value. Now we're going to try to show you exactly how to use that to see if a hypothesis test is going to reject or fail to reject that guy. So let me just write it down. It's not going to make a lot of sense at first, but I promise you that it will in a few minutes. So basically, here's how you use a p-value. So I'm going to write conclusions of the p-test. In other words, we told you at the beginning of the day here, or the beginning of the last couple of lessons, that the p-value is still going to be used to tell you when you reject a hypothesis or fail to reject a hypothesis. It's doing the same job that we did before in a slightly different way. All right? So we have a criteria here to tell you when you reject a null hypothesis and when you don't. And they're very, very simple. If the p-value, which we call p, is less than or equal to alpha, this is the level of significance that we have in every one of these hypothesis tests, then you reject the null hypothesis. Very simple. If the p-value that you get is less than or equal to the level of significance alpha, then you reject the null hypothesis. If the p-value is greater than alpha, it has to be greater. If this is less than or equal, the only other choice is that it would be greater, then you fail to reject the null hypothesis. So this is basically the most important thing we're going to say in this lesson. Now, I'm going to tell you right now, when I first read this, when I said, well, if p is less than this, we reject it. And if p is greater than this, then we fail to reject it. When I first read that, maybe the first 10 times that I read that, I did not understand intuitively why this would lead to rejecting the null hypothesis and this would lead to failing to reject the null hypothesis. And your book, most cases, are not going to explain it to you. They're just going to say this is what a p-value is, and this is what it basically, it's the probability of getting something more extreme than your sample data, okay? And then they're going to tell you, well, if the p-value is less than the alpha, then you reject it, and if it's greater, you fail to reject it. Now, you could just blindly follow that. I mean, I could give you a problem right now. I could say, here's the null hypothesis, here's the research or alternate hypothesis, here's your level of significance alpha, and then here's your data. You can calculate a p-value. We've done it in the last couple of sections here, and then from that p-value, all you do is you compare it to the value of alpha, and then it gives you the two cases in which you reject or fail to reject. We could do that right now, but you wouldn't have any intuitive understanding of why, right? Sometimes it's worth it to talk about why, and sometimes it's not really so worth it to talk about why. Now is one of those cases where it is worth it to talk about why this is the case. The first thing that you have to remember is that these criteria, I know you can't see it until I draw a picture, these criteria on the board, it is exactly the same as what we've been doing before with the rejection regions. And when I mean exact, it is literally exactly the same thing. This is not a brand new test or a brand new class of hypothesis test or a brand new concept, really. It's just kind of a different angle on what we've already been doing before. The rejection regions really are always there. We're just using the p-values here to do things in a slightly different way. Now I want to prove that to you. I want to prove that these kind of criteria here leading to rejection or failing to reject is exactly the same as what we have been doing before. So in order to show you that, I need to go through a couple of scenarios. So the first scenario is going to be the very easy one. Let's talk about a right tail test. We've been doing a lot of these. We did them for the t-distribution. We did them from the normal distribution. You know the basic idea. Forgetting about p-values, you know the basic idea of hypothesis testing, right? You have a level of significance. It's a right-tailed test. You have an alpha shading in the right-hand tail, and then you have a test statistic. You calculate wherever it falls. That tells you if you're in the rejection region or not. Do you reject a null hypothesis? So let's go and look at that in this particular case. And I'll show you that these p-values are basically doing exactly the same thing that we've always been doing. You know, that's what's kind of frustrating sometimes with books and with teachers even, is that you learn this p-value stuff after you've learned the rejection region, and you think this is totally different. It's something new. Well, in fact, it's really not. It's going to be essentially the same thing. So let's say this is a z-distribution, always centered around 0. You already know that. Forget about p-values for a second. Let's just pretend this was a typical hypothesis test where we're doing a right tail test. Well, you're always given a level of significance. You know, you always are. Or you're given the level of confidence. You might be told 95% level of confidence, and you know from that that C would be 0.95 and alpha would be 0.05. But in any case, no matter if it's 95% or 98% or 92%, you're always given either the level of confidence or the level of significance. You always have to be, right? So in this case, let's just pretend that we're given that level of significance alpha. And so the very first step in all of these hypothesis tests for a right tail test is to go over here and shade some right tail over here, and we say that the area here is alpha. We say that the area here is alpha. And from that, I'm not going to draw them on the board because we've done it so many times, and I don't want to clutter up the drawing, but you know that basically this is going to be some critical value of z here, right? You can also think back to the t-distribution. This was t sub alpha, but anyway, there's a critical value of z if it's a z-distribution, it's critical value of t if it's a t-distribution. It's just the value of z in this case that gives you an area of alpha to the right. Alpha might be 0.02, alpha might be 0.05, alpha might be 0.10 or whatever. It depends on the level of confidence, level of significance of your problem. But we know that this is just a number, represents the area. And we know that this defines these rejection regions. Okay, if you draw a dotted line here and we calculate our test statistic, remember that comes from our sample data, we get a value of z. If that value of z lies anywhere to the right over here, then we say that it is so strongly statistically significant that we can reject the null hypothesis. Remember, the null hypothesis is kind of sitting in the middle of the distribution, and then we need to get far enough away from the null and trip us over into the rejection region so that we're comfortable saying that, at that level of confidence we can reject the null hypothesis. But if the test statistic, even if it goes this direction, if it doesn't get that far into the rejection region, if it stays anywhere over here, then we say we fail to reject the null hypothesis. Those concepts, rejecting, fail to rejecting, those rejection regions should be in your head. Even if you don't label it every time you draw this guy, they should be in your head. We've done it so many times. Right? So here, forward, we reject. Here, backwards, we fail to reject. Okay? So the way that we would work this problem if it were a regular hypothesis test, not p-values, we would put our alpha, we'd shade the right tail, we'd find the critical value here, which would be a number in terms of z, and then we get our test data, we calculate the test statistic z, and we would see if it falls here, and we would see if it falls here, and that tells us if we reject or fail to reject. Okay, that's a bunch of talking about stuff we've already done. Now, let's apply the new thing. All right, here's where we need to talk about p-values, okay? Let's pretend for a second that the value of z that we get from the test statistic from our data falls over here. Let's just pretend. So let me put a little arrow right here. Let's say that the value of z falls in there, right? That comes from our data, that comes from our sample data, right? You could say sample mean, you could get a sample standard deviation, number of samples, we calculate z, it falls here. We know that we reject the null hypothesis in that region. Obviously, it's in the rejection region. Okay? But also, this is the value of z that's representative of our sample data. And we just talked about in the last section, we just said that the p-value is the probability of getting a data point more extreme than the data that you collected. This value of z represents our data. This value of z is just the threshold we have to cross to pass or fail the test. But this value of z is in the rejection region, and it represents the data that we have. So if I wanted to find the p-value of this data, I would go and look at this value of z that comes from my data, and it would be everything to the right. I would be shading everything to the right because it's more extreme. In this case, it's a right-tailed test, and that would be more extreme, right? So if I wanted to find the p-value, I'm not going to do it because I don't want to destroy what I've done here. I would draw a dotted line, and I would shade everything to the right. Okay, so in this case, the p-value would be this area over here, right? So p would be less than or equal to alpha, right? Alpha is this whole shaded region, and if we were rejecting the null hypothesis, the p-value would be smaller, right? The p-value would be smaller than alpha, right? So when z is here, when z falls in this region, p is less than alpha. And this means, based on our little test, p is less than alpha, we reject the null hypothesis. Reject the null hypothesis. So you see how these two concepts are saying the same thing, right? If we define an alpha and we put it here, right, and then if we go and find the test statistic and see where it falls, does it fall in the rejection region or not? We can see if it's rejected. Here we said, okay, the data falls in here, it's rejected. Well, if it falls in here, then the p-value's got to be the area to the right, which is less than alpha, which also points to a rejection. So you see, whenever you use p-values to determine if you're rejecting the null hypothesis or not, it's exactly the same thing that we were doing before. You see, the z-value has to fall here in order for the p-value to be less than alpha. It has to fall in the rejection region. It has to be somewhere over here because the area to the right of my value of z for my data is going to be what the p-value is. So in order for me to reject, the area has to be smaller than the area of the level of significance. Likewise, if I go over here, let's pretend we do it totally. This is one case. Now let's say that we set this problem up and we get our test statistic back from our data and the data falls somewhere over here. Right? So let's say that we call this z data over here. Well, we know from experience that the rejection region is over here, and if it falls anywhere over here, we fail to reject the null hypothesis. Now, if the data did fall here, what would be the p-value? I would draw a dotted line up from this value of z up here, and the p-value would be shaded all the way to the right in the direction of my test, right? More extreme than my data here. So in this case, p would be greater than alpha because the area from my data to the right would be greater than the level of significance alpha. So I would, because p is greater than alpha, I would fail to reject. H naught. I cannot stress enough to you how you really need to understand this, all right? I would not take time to talk about it if I really didn't think it was important. Okay, you can just blindly follow this. It's true, you can. You can find the p-value, you can see if it's less than alpha, and then you know it's rejected. That's cool. That's really what you're going to be doing in all the problems. But to intuitively know what it's telling you, and that it really is exactly the same thing as what we've been doing before, is really what I really wanted to tell you here. Now, let this percolate. I want to show you a left tail test. It's a little bit redundant because it's going to basically look very similar, but I want to make sure that you understand this. So let's look at left tail test. Now, if we have a left tail test, everything's going to be the same, except obviously we're going to be dealing with the left-hand tail instead of the right-hand tail, but the concepts are going to be exactly the same. If I have a level of significance, and I'm doing a left tail test, the way I do it is I'll lock down this level of significance here. We call it negative z sub c. The shaded area to the left we call the level of significance. You're always going to have this for every problem you do in a hypothesis test, right? At least at this level, what we're doing right here. The critical value of z, we know how to get that. We've tabulated that before. That gives us the area to the left here. Now, let's go and look at the two possibilities. In this case, if I get a test statistic anywhere over here, I'm going to reject the null hypothesis. If I get a test statistic anywhere over here, I'm going to fail to reject the null hypothesis. Now, let's just say, for some reason, that I get my sample data, I calculate the test statistic, and I get a number that's in this region over here somewhere. Let's say maybe over here, right? So I'm going to say this is z data. This comes from the data. This is the test statistic that comes from the data. So what would be the p-value associated with this data here? Well, I would have a dotted line here, and it would be the probability of getting a data value more extreme than the data set that I have, which would be an area from here to the left. So this means that, again, p would be less than or equal to alpha because of the fact that if I'm in the rejection region here, then by definition, the p-value has to be less than alpha. Another way to look at this is to say if your data test statistic that you calculate really does fall in the rejection region like it does here, then it has to be true that the p-value has got to be less than alpha, because if the p-value was greater than alpha over here, which is really what I'm going to talk about next, if the p-value over here if the z data, if your value of your test statistic was here, then p would be greater than alpha, because in that case, the p-value would be a dotted line up here and all the values more extreme than that. The area would be greater for that p-value as compared to this. So in this case, everything lines up again. We reject the null hypothesis in this case because the test statistic falls in this region, but also when you think about in terms of areas, the p-value, the area here, is less than the level of significance here. And also over here, we fail to reject the null hypothesis. Again, because the p-value here, the shaded area from this point all the way here, is greater than the level of significance. So I'm doing this to you because honestly, whenever I first looked at these two rules, I mean, you can simply just follow them. I mean, really, and ultimately, really all you have to do is follow it. You find the p-value, is it less than alpha? If it is, you reject. If it's greater than alpha, you fail to reject. You can just follow that. But you know, you're going to eventually get stuck on a test. You're going to confuse yourself if you don't know what a p-value is doing. It is exactly the same as what we've been doing before. You need to start thinking about the p-value representing a little slice of area here compared to the area of the level of significance. So if your p-value is smaller than the area of your level of significance, that means that your data must be falling in the rejection region, so you reject the null hypothesis. If your p-value is bigger than the area that you have in the tail, that means that your test data must be outside the rejection window. Okay, so I think, hopefully, I've given you at least some kind of understanding why p-values do exactly the same thing as rejection regions. There really is no difference between the two concepts. One of them is looking at the value of z and where it falls. The other one is just looking at the area of the p-value compared to the area of the level of significance, but they're giving you the same results. Okay? The question then is, everybody should ask, why do we learn p-values? I mean, didn't the rejection region work perfectly fine? I mean, we were doing all these problems, we were solving them, everything was great. Why did we stop and invent this new thing, which admittedly is the same thing, but in this kind of different way of thinking about it? Why do we even do that? And why is it more common to see that in real-life statistical papers? The answer is, I just have a sentence here, I'll tell you, it lets you choose the level of significance alpha that you need to reject the null hypothesis. I'll say that again for you because I don't think when you say it the first time it kind of sinks in for you. Basically, whenever you use p-values, it lets you easily choose your own level of significance alpha that lets you reject the null hypothesis. Think about it for a second. Why do you think people do hypothesis testing? Okay, if there's an established null hypothesis in some factory that the candy bars come at a certain length, right? And I come in the door and I think, just by kind of looking and eyeballing it, I think that that null hypothesis is wrong. So I propose a new hypothesis. We call that an alternate or a research hypothesis. So I propose that, and I want to go into the meeting and be a rock star and say, look guys, I showed you that the candy bar machine doesn't work. They're making the candy bars too long. Okay? Well, the way we've done all of the problems so far is I've specified a level of significance, which you can think of as a level of confidence. I've said at 95% confidence, I want to see if I reject this null hypothesis or not. And I told you many times over, in fact, every problem I said, hey, when I reject a null hypothesis or I fail to reject a null hypothesis, it's only valid at that level of significance, right? Or that level of confidence, 92% level of confidence, 97% level of confidence. And I told you if you move that level of confidence around, if I start playing with alpha, I can basically get it to accept or reject. Generally, I can kind of make it do what I want. So think about it for a second. You're the new employee, you go into the new company, and you want to show these guys that you know what you're doing, and you think the machine isn't working right. So why would you choose 99% level of confidence? I mean, what if you choose the wrong level of confidence? If I choose 99% level of confidence and I fail to reject the null hypothesis, then I haven't done anything. I mean, I'm not able to go to the boardroom and be all awesome and tell them how I found their problem. That's because I maybe set the level of significance or the level of confidence a little too high. So what would I then do? I would back it on down. I'd say, well, let me do it at 97% and see if I can reject the null hypothesis, because I'm the guy that proposed the alternate hypothesis, right? And let's say I do it at 97%. And again, I was not quite able to reject that null hypothesis. Well, then I pop it down to 94%. maybe 95% didn't work. I pop it down to 94%. You see, every time I move the yardstick or the goal line is what I'm doing. I'm moving the goal line. When I change the level of confidence, I'm moving the threshold point so that my data is staying fixed. The data that I collect stay fixed, but when I move the goal line, I may end up in the rejection region if I can move it back far enough. All right, so here's the deal. If I were to do it the old way, the way in which you learned with rejection values, then I'd have to start, or rejection regions, I'd have to start at 99% level of confidence and see if I reject or not. And then I'd go to 98, and then I'd go to 94, and then I'd go to 92, and then I'd go to 90, 91. And then maybe at 91, finally I can reject the null hypothesis. Okay, so I go into the boardroom and I say, guys, I'm 91% confident that your machine's not working, and everybody's impressed. Well, you see, that work was kind of cumbersome. I had to do the test several times. I had to do the calculation several times, starting at a high level of confidence and working backwards to get it to finally reject the null hypothesis. All right, all of that's a backstory. When you use p-values, you don't have to do this kind of manual monkeying around with the goal line. You kind of already know it from the p-value. And let me explain what I'm talking about. Let's say that in my little hypothetical scenario, I'm the new employee, and I'm doing a right tail test. Right? Because I'm thinking, for instance, the candy bars are too long, right? So if I'm doing a right tail test, and this is a normal distribution like we're always doing at this point, so I put, Z here, and right in the middle is 0. So it's a right tail test. Usually the way we've been doing it in the past is I take my level of significance here, I shade it, I label this as alpha, and I say, hey, here's the rejection region, and I've showed you how p-values are basically compared to the level of significance to figure out if you fail or you reject or fail to reject the null hypothesis. But let's just say I'm doing a right tail test because I think these candy bars are actually too long. So I'm doing a right tail test. I think the candy bars are greater than 10 centimeters or something. I have a greater than symbol, so I'm doing a right tail test. I collect 32 candy bars and I measure them, and I get their average length. I get the standard deviation of the lengths. I know the number of samples. I know what the null hypothesis is, so I can roll all of that stuff into the test statistic z, and I get a value of z back. And we already said that I can take this value of z. This comes from my data. I'll just put a little reminder, from data. Right? And I told you, how do you find the p-value? Well, I can come here, and you are looking for values more extreme than the data that you have. Here's my data. This is more extreme because I'm doing a right tail test. All right? And so this shaded region here, is what we call the p-value. And we know how to look that up, right? I can look this up because I can look in a z distribution table or a normal table, and I can figure out what the area is to the right of this value of z. Now, this comes from my data. This has nothing to do with the level of significance. This comes from my data. So the question then is, if my goal is to look good in front of a company, I want to reject the null hypothesis. I want to go and see, hey, what level of significance do I need in order to reject this stinking null hypothesis? Because I think the machine is not working right. I don't know exactly what level of significance I need to prove my point, okay? But then I remember, hey, wait a minute. When I'm dealing with p-values, I reject the null hypothesis if the p-value is less than or equal to alpha. I'll say it again, if the p-value is less than or equal to alpha. I'll say it again. You can reject the null hypothesis if the p-value is less than or equal to alpha. So, for instance, let's say that this p-value, let's just pretend this p-value that I get from looking this stuff up in a book or in the table, it comes out to 0.12. That's the area to the right of my value of z that I get there. Let's say that I find that p-value. Okay, I know that I can reject the null hypothesis. I can reject the null hypothesis, which is what I want to do if I want to look good in front of a boardroom, if p is less than or equal to alpha. Notice it says or equal to alpha. So then all I have to do is then say, aha, well then I'll say alpha is 0.12. 0.12. And then from that, c is 1 minus alpha, 1 minus 0.12, 0.88. So the level of confidence is 88, in this case, percent. So you see, instead of starting at 99% and then seeing if I fail the test or if I can reject a null hypothesis, and then going back to 95 and 94 and 93 and going back and back and back until finally I can actually reject a null hypothesis, all I have to do is put my data in the thing, and I find the p-value, which is the data more extreme to the right, and then I can say this p-value associated with this set of data that I got was 0.12, and then from that I can say that alpha is 0.12 because I can reject if p is less than or equal to alpha. In other words, if alpha were defined to be right here, right on top of my value of z, then alpha would be exactly equal to the area of the p-value. They would be lying both on top of one another. And since I write it like this, I'm basically saying that that's the threshold when I can reject that null hypothesis. Clearly, if the alpha is over here, like if the critical value of z is over here and alpha is this entire shaded region here, let's say from here, then the p-value is less than alpha if I'm over here, and I can reject the null hypothesis. But if I move my yardstick closer and closer and closer, eventually alpha is going to equal the p-value, and when those things are equal, I can still reject it. Now, if I move my level of significance too far in, then I go on the other side, the level of significance is going to be smaller, and then I can't reject it anymore. So the reason why in real life people use p-values is because generally people are trying to disprove something or to reject a null hypothesis. If I'm doing a survey and I want to print results, generally I'm trying to dispute or to contradict or to go against the null hypothesis, and what I really want to do is prove that that's true. Now, of course, you have to specify the level of significance or the level of confidence that you do that at. So what you do is you collect your data. You don't specify the level of confidence ahead of time. You collect your data, calculate the test statistic, calculate the p-value, and then that tells you right there what level of significance you need in order to reject the null hypothesis. So what I could then do is go into the boardroom with confidence and say, hey, I took 35 candy bars off the line, I measured their mean length, I did the standard deviation, I did all this stuff, and I figured out that I'm 88% confident that we can reject that null hypothesis, and I think that the candy bar machine is making candy bars too long, and I'm 88% sure. Now, to most people in a boardroom, 88% is pretty decent level of confidence, but in statistics, you really need something a lot higher in order to have high confidence. At least that's my opinion. I don't think a lot of people are going to be terribly impressed with this, but it's very easy to convince an average person that 88% confidence is pretty good. I mean, if I had an 88% chance of winning the lottery, I'd be pretty happy, right? Obviously. So keep that in mind. Now, this entire discussion of why we use p-values, you probably aren't going to see too many problems like that. I just wanted to show you that that is why p-values are useful. Why did they go through the trouble of creating these p-values? The main thing that you need to pull out of this lesson is that if the p-value you get is less than or equal to the level of significance, you can reject it. You can reject the null hypothesis. If the p-value is greater, you can fail to reject the null hypothesis. And we have gone through those different scenarios, and I hope that I've shown you with graphical methods why this stuff is exactly the same thing as our rejection regions before. All right, now we've got all this groundwork laid. Now we can go off into the next section and work some problems. And I think that as we solve more and more problems with p-values and kind of making these determinations, you'll understand how it all works when we solidify it with a lot of problems. We haven't really worked a lot of problems yet. What I've done is very conceptual. So follow me on to the next lesson, and we'll do some real problems. We'll get a lot of practice with p-values, and now you also know why p-values are useful. It's because people like to develop cases when they can reject their null hypothesis, and the p-value tells you what level of confidence you can do that at. It tells you what yardstick, what goal line you have to be at to reject the null hypothesis. So let's go on to the next section. We'll work some additional problems in hypothesis testing with means with large number of samples, where we're using the p-value to determine if the hypothesis, the null hypothesis is going to be rejected or not.